Now we're going to find the generalized formula for the distance between a plane and a point. In the previous video we do a exercise, and to have the generalized concept, now we're going to find the generalized formula, but I didn't do it in the previous video. I realized that we have already 12 minutes in the previous video, and this video is also going to be like 10 minutes, I guess. So let's do it in separate videos. Alright, so we have a plane, we have a point, and we want to know this distance. In the previous video we saw that if we pick a point P naught, we find this vector, and next we do the scalar projection of this vector onto this vector. We will have the distance. Now this vector is the normal vector to the plane. Is you have the point, the plane, this distance is in the direction of the normal vector to the plane. So the normal vector, here I have the same example, but if we do it in generalized way, we have ax plus by plus c equals d. And this is the equation of the plane. In this case, is 3x plus 2y plus 6c equals c. So the normal vector, as you know in this, is 3i plus 2y plus 6. Okay? Here, the normal vector is ai plus bj plus ck. This is the normal vector, the generalized equation of the normal vector. Next, the point, let's say this point P, that is in the example 1, 1, 1, 3, this is x naught, x1, y1, c1. And this point that we're picking, we already know that it's easier to pick the intersection between the plane and the axes, but here the generalized coordinates of this point is x naught, y naught, c naught. Now the vector PO, P1 is x naught minus x1, y naught minus y1, c naught minus c1. This is the vector. So you have the vector is, you have P of P1, you have x naught minus x1, I plus y naught minus y1 j plus c naught minus c1 k. And now we want, remember, in order to find the projection, the scalar projection, you know that P of P1 dot n is equal to the magnitude of P of P1 times the magnitude of n times the cosine between the two angles. The scalar projection of this vector onto this is just the magnitude of P of P1 times the cosine of theta. So you divide the dot product divided by the magnitude of the normal vector. That is, you could say the dot product between this vector and the normal vector divided by the magnitude of the normal vector, or you could say that you are dotting the vector P of P1 with the direction of the normal vector. That is n divided by the magnitude of n. Alright, anyway, so you have the magnitude of n. Magnitude of n will be the root of a squared plus b squared plus c squared. So you have this this normal vector dotted this vector divided by this, or you could say this vector dotted this divided by this. Anyway, you will have, remember, a x naught minus x1 plus b y2 y naught minus y1 plus c naught minus c1, so times c, all this divided by the square root of a squared plus b squared plus c squared. As you can see, when you multiply a times x1 plus b times y1 plus c times c1, you have the distance, the constant x not x1 not. You can put it this way, or this way is as I do it, but I think that it's easier to understand. Remember that the vector PO to P1 is the same as P1 PO, so you can change this. Instead of putting x naught minus x1, you can put x1 minus x naught. So x1 minus x naught, y1 minus y naught, and c1 minus c naught. So here I will change them. Remember, it's the same thing, and you will see why. X naught minus x1 is 1 minus x naught, 1 minus y naught, and c minus c naught. Now, you know that you have this plane, the plane ax plus by plus cc equals d, and that the point x naught, y naught, c naught lives in this plane. As you remember, when you have a point and a normal vector, you can find the equation of the plane. That is, this equation of the plane came, you can say, from the normal vector 3i plus 2j plus 6k and the point 0, 0, 0. And this would be that, or whatever point you, 0, 0, 0,6, for example. Whatever. The issue is that, as you remember, the equation of the plane is ax with ax plus by plus cc equals d, or you could say it is ax. We use ax minus x naught plus b times y minus y naught plus c times c minus c naught, where equals 0, whereas x naught, y naught, and c naught are the equation of the point that lives in the plane. So this was in the video in which we find the equation of the plane that passes through this point, or that contains this point, and given the normal vector. Alright, well, but you recognize that this is the equation of the plane. We put this in this because here you have ax, by, cc, and this d is ax naught, b, y naught, and c, c naught, with plus sign because we are sending them to the right side. So here you have exactly that: a, x naught, b, y naught, c, c naught. So you have, this is ax plus by plus c, c, x1, b, c1, Remember, this is not ax, this is this x1, the y1, and c1 come from this point, are the coordinates of this point. So it's this divided, minus d divided by the square root of a squared plus b squared plus c squared. Alright, so now let's calculate. We already know in the previous example we find this is the square root of 9. The normal vector is 9. Well, this is the normal vector, so you have square root of 9 plus 4 plus 36. This was 7. And here we have 3 times 1 is 3 plus b, that is 2 times 1, that is 2, plus c, that is 6 times 3, that is 18, minus d, which is b. d is equal to a x naught plus b y naught plus c naught. Let's take this point. We took this x naught, we put the y-intercept that was 0, 3, 0 in the previous example. You know, if you put 0 and 0, you have y equals 3. So that is the y-intercept. So here would be d will be 0 plus b, which is b. b is 2 times 3 is 6 plus 0. d is 6. So you have 3 plus 2 plus 18 minus 6. You have 5 minus 6, minus 1, 18 minus 1, 17 divided by 7. And you got exactly the same result as we got in the previous example when we do it more structurally. Here we find the generalized formula and then we find just the knowing the normal vector or finding the normal vector from the equation. We calculate the magnitude. Here we have the coefficients of the normal vector multiplied by the x1, y1, c1, that are the coordinates of the point that we're going to find the distance between this point and the plane, minus d, that is the coefficients of the normal vector multiplied by the coordinates of a point that we know that lives in the plane. Again, we want to find this point that is it's easier to find the intersection with the plane and one of the axes. Essentially, you are finding exactly the same things. Here you can memorize the formula, and it's exactly the same. You do dotting the vectors. You need to find this vector. You need to find from the equation. The normal vector is exactly the same. Anyway, you can view it. You will have the same result.